So it's great to have this distinguished panel here. And I'm going to briefly introduce all of you and then ask actually the same question that I just asked the solar panel, and you can give some opening remarks. I think you've seen the focus in solar energy on reducing costs. That's important to be able to scale these technologies, provide affordable electricity to all people, and to bring down carbon emissions. So that's very important. We need to bring down costs in energy storage as well, and certainly to be able to support the use of renewable energy as part of the mix, as a large part of the mix for supplying electricity and decarbonizing the electricity system. So our panelists will address a number of diverse topics in this area, and they've been doing some fascinating work and really blazing new trails in the development of energy storage technologies through laboratory research and investment and so forth. So just briefly to introduce them, we have Yetming Chang, who is the Kyocera Professor in the Department of Material Science and Engineering here at MIT. His work focuses on advanced materials and energy storage technologies. He's published about 300 scientific papers and holds over 80 US patents, of which more than 60 have been licensed or held by practicing companies. He's a member of the US National Academy of Engineering and has received the Economist Innovation Award, among other awards. And he's a co-founder of the companies Forum Energy, Desktop Metal, 24M Technologies, A123, among others. Fikili Bruchette is an associate professor in the Department of Chemical Engineering here at MIT, and he holds the Cecil and Ida Green Career Development Chair. And his work seeks to advance the science and engineering of electrochemical technologies that enable a sustainable energy economy. He's especially interested in fundamental processes, but then also looks at how those fundamental processes define performance, cost, and lifetime. So these really practical dimensions that we care about of current and future electrochemical systems. And his group works on redox flow batteries, among others. Yang-Xiao Horn is the W.M. Keck Professor of Energy in the Department of Mechanical Engineering, Department of Material Science and Engineering, and she holds also an appointment in the Research Laboratory of Electronics. And her work is centered on exploiting physics, chemistry, and material science to understand charge transfer at the solid-gas-liquid interface, to design and control the kinetics of electrochemical reactions, to store electrons and make fuels. And she's pioneered new approaches to making sustainable solar fuels using water splitting, CO2 reduction, among other approaches. She's a member of the National Academy of Engineering and was awarded the Faraday Medal by the Royal Society of Chemistry, among other awards. David Danielson is the managing director. It's really hard to keep these bios short, as I'm sure you can see, but I'm doing my best to touch on the highlights. David Danielson is the managing director of Breakthrough Energy Ventures. Previously served as the assistant secretary of the U.S. Department of Energy's Office of Energy Efficiency and Renewable Energy, thank you for that, where he led the largest government clean energy innovation funding agency in the world at this EERE, as it's called. He directed the government's innovation strategy in the area of sustainable transportation, renewable power, energy efficiency, clean energy innovation, and investing about $2 billion annually into clean energy innovation here in the US. He's an expert in the development of next-generation clean energy technologies, among other things, and was a very successful employee at ARPA-E, at DOE, for those of you that know that. He was also the founder, for the students here, and president of the MIT Energy Club, and received a PhD here at MIT in material science. Okay, so just quickly asking you a question. What are some of, again, the same one as before, what are some of the most consequential recent developments in the area of energy storage, broadly defined? This is a very diverse set of technologies. We're going to do our best to touch on this diverse set. And what are some of the most important unsolved problems? So we'll ask these questions, ask for your remarks, try to keep them short so we can take some questions from the audience. But yeah, let's start with Yetming Chang.
Thank you. So I drew the short straw. I could go first. If you look at grid storage, we're primarily going to talk about storage for electricity, but I want to first touch on lithium-ion and what's been going on in lithium-ion. because over 90% of the grid storage installed over the last couple of years has been lithium-ion. And so we frequently are asked the question, what is the future for lithium-ion, right? And so in a way, betting against lithium-ion I think is a fool's bet. Right? This is a technology that's 30 years old, has systematically improved in performance 8% a year. The cost down curve has gone much faster than that, about 90% over the last 10 years. And the Nobel Prize Committee is giving batteries some love finally. All right? So this year's chemistry prize was to 3 individuals who were pioneers in lithium-ion and did their work over a period of 20 years. Right? So if you're reading newspapers, you may hear that the price of lithium-ion battery packs continues to drop. Right now, it's about $160 a kilowatt hour. Right? The energy density continues to go up. Right? So I'm going to tell you there are great things going on with lithium-ion, but then I'm going to tell you why it won't do everything for us, especially in terms of grid storage. Right? Amongst the other drivers that are really pulling us along in developing better lithium-based batteries, if not specifically lithium-ion, are things like electric aviation. So next week, I'm at a workshop where now the DOE Vehicle Technologies Office has concluded that aircraft are, in fact, vehicles. Right? And so we have a workshop on batteries for electric aviation. Right? So much is going to go on there. To say something about why that's not going to do everything we need to do, if we take this target of $100 a kilowatt hour, which is where many people think the EV battery pack will get to in a few years, the grid storage based on lithium-ion will be roughly $50, $75 a kilowatt hour more than that, just because there's more hardware involved. But let's take that $100 a kilowatt hour. If we're able to use that battery over its life, 10,000 cycles, charge it up and down 10,000 cycles, the electricity that it delivers is 1 cent a kilowatt hour. And we might all agree that that's a pretty good number. Right? So there's a problem here, which is that these batteries don't last 10,000 cycles. Right? And so if we were to use it once a day, the 10,000 cycles is 27 years. The calendar life of that battery today is about a third of that. Right? And so lithium-ion will continue to be a great technology for grid storage as long as we use it a lot, cycle it up and down all the time. Right? Now, the kinds of problems we're facing even today, I'm going to take an example. Well, first, we all know about what's happened in California recently. But I'll take a slightly different example. In the upper Midwest, in Minnesota, there's an electricity co-op called Great River Energy. And over the last couple of years, their biggest storage problem has been in relation to the polar vortex. It's gotten so cold that the lubrication has frozen in the windmills and the windmills won't turn. Right? When that's happened, it's been an outage of several days. Right? MISO turns on all the peakers, right? And there's still a shortage. Right? And so there you have a need for a battery that might be used relatively infrequently, but in order to achieve the levels of reliable electricity we become used to, not what we have in California today. Right? So in order to have a battery that can still deliver that very low cost of electricity, a cent or so a kilowatt hour, but is used over longer durations and less frequently, the capital cost has to come much farther down. Right? And so that's why there's a need and a great deal of activity in new chemistries. And so one class of these new chemistries are materials that I would call highly abundant inorganic materials. Right? Sulfur is one of them, one of my personal favorites. Another would be zinc, for example, right? Not likely to be resource constrained. And so in comparison to lithium-ion, where just the chemicals alone to carry out the storage might cost us something on the order of $25 or $30 a kilowatt hour. Now we have alternative chemistries being developed, none fielded in large volume today, which are in the single digits, in some cases $1 a kilowatt hour or less. And so we're moving towards a new envelope of electrochemistries for grid storage. One of the great components to use with these very low-cost elements is air, right? Highly abundant, not likely to be resource constrained. And so batteries that actually use air as one of the reactants are very attractive for a variety of reasons. They have not been successful in applications like electric vehicles because the electrodes that carry out those electrochemical reactions with air, oxygen really, are rather inefficient. And so a battery of that type that uses sulfur in air or metal in air might have a round-trip efficiency that's, say, 50 to 70%. Lithium-ion is about 95%, right? So you'd say, well, isn't that a terrible battery? But what's going on is that the cost of electricity is dropping so far that we can begin to tolerate lower round-trip efficiency energy storage systems. They're all still much better than a gas turbine, right? And so that's the direction that we're going in which these much lower cost, highly abundant chemicals are the basis for new storage systems. And I think Fikile will have other examples in this realm.
Yes, thank you. So kind of building on the same theme that Yet just started on, when we think about a lot of the battery technologies that have been developed over the past 30 or so years, they've been largely based upon portable applications, so things to go into portable electronics, things now to go into vehicles. And so that pushes you towards more energy-dense chemistries because you want to be able to store as much energy in as small a space as you can. When you start to think about more grid-related technologies, what you're banking on more is cost and lifetime, and you're willing to give up a little bit in terms of energy density. What that does is not only open up the room for more chemistries, either chemistries that have been overlooked previously because they didn't fit a previous application space, or even new chemistries that we might not have considered beforehand, excuse me, is we can also start to think a little bit more about new design spaces. So rather than thinking about putting chemistries in a very small sealed container, maybe the chemistries that you want to use look a little bit more like a chemical plant. Maybe you want to introduce flow. Maybe you want to introduce, new inputs and outputs like an air-breathing electrode. This leads to new design questions, and that's an exciting part about being in the research community, where we need to start changing our focus to sort of saying, instead of saying, I have a lithium-ion battery, how do I begin to squeeze a little bit more performance out of it, to what is the application that I have in mind? What am I interested in? And then what chemistries might fit into this portfolio? And what are the problems that arise with those particular chemistries? And really, the important part to remember is that these are energy storage systems. And each of these systems have multiple components associated with them. So simply focusing on one component and trying to optimize it as best you can may not actually result in the best possible system. So understanding how all of the components will interact with one another, and what combination of components or what property profile may lead to the lowest cost or most useful energy storage system is a new way that we need to start thinking about it in the research community. And the reason that that's relevant comes up in a previous comment made in the panel before us, which is the scope and the scale of these kind of changes that need to be made are tremendous. Couple on that the sense of urgency, how quickly these changes need to occur. Materials need to be discovered and developed and moved very quickly through an innovation pipeline. That innovation pipeline needs to be kept full, and all of this requires a need for us to be able to discover and develop new materials more quickly and to be able to down select between different materials much more quickly. And the way to do that is to essentially try to pull on the larger research community. So there are lots of people who wouldn't consider themselves to be battery scientists, wouldn't consider themselves to be battery engineers, but have useful insights to bring to the table. They just need to understand what the problem is, what we're looking for. And so finding ways to be able to communicate to the greater research community will be an important next step to getting essentially more hands to the pump and helping driving us forward. So one example I'll give is the role of organic chemistry in all of these types of applications. When we think about new redox active materials, as Yet mentioned, we can think about abundant inorganic materials that are readily available. But in many cases, the properties of those materials are fixed. And so you hope you find the right material to meet the application you want. For organics, there is a possibility through chemistry to begin to tweak properties that are desirable, to change the energy density, to change the solubility, to change the redox potential, to change the stability. And there's a whole host of communities that know and understand how to work these materials quite well and how to derive materials that have the properties that we want, potentially at the cost points that we want. And so being able to access that community and focus them in on some of these problems will hopefully help us to move forward a little bit more quickly.
Great, thank you. And that was Yetming Chang and Fikili Burchett and Yang Xiaohorn. If you could give us your thoughts, please. Thanks.
Good afternoon, everyone. First, I want to thank Paul and Jessica for chairing the panel. So I agree with my colleague Yet and Vic's point of view, and I'd like to add a few more different perspectives. So first is really the needs or consideration for material sustainability and the recycling of batteries going forward. As you have seen from the graph shown by Paul, also the comments made by Yet, there's tremendous growth, projected growth for lithium-ion batteries in electric vehicles. Based on IEA report of 2018, we're expected to have 100 times growth in electric vehicles in 10 years. In addition, there are also impressive growth projected in the electricity or grid sector. Right. Currently, most of batteries, lithium-ion batteries, utilize cobalt, and that essentially take 50% of the cobalt we use today. And there's a notable change of changing cobalt chemistry to nickel. So we see that shift in lithium-ion batteries to come. Right. So there's a question of what is really the materials needs or material sustainable perspective. Can we sustain, the nickel growth or production in need of electric vehicles and in need of lithium-ion batteries for grid applications? In addition, we want to consider alternative chemistry. So if you look at sodium-ion chemistry offers a potentially equivalent energy but lower cost. And the elements utilized in sodium-ion batteries are more earth abundant. So can sodium-ion batteries be used for applications related to utility or service vehicles or grid applications? Now, cobalt and nickel, ultimately, really among relatively rare elements, right? Can we utilize elements that really in our Earth's crust, more like iron or manganese, silicon to store the electrons we have today in lithium-ion batteries, right? So can we develop even more inexpensive, low-cost material, iron-based or manganese-based for storing lithium-ion batteries? So when we have a large amount of batteries, right, so from electric vehicles, can we predict the lifetime or the second lifetime of lithium-ion batteries? Can they go from EV applications to, for example, grid applications? Right? How do we really predict the lifetime and to increase essentially really the utility of these materials for a given use? And what about battery cycling, right? So what we're going to do with all the used up lithium-ion batteries from our electric vehicle sector and grid sector. And I think these are really the challenges to consider, to address in the coming decades or more. The second, I think, really exciting opportunity I want to highlight is related to energy carriers, right? Especially metal-based, hydrogen-based carriers. 2019 is a year of hydrogen, right? So there's tremendous opportunities to utilizing the low-cost electrons to make new chemical bonds, to make metal-based, for example, aluminum-based or zinc-based or lithium-based energy carriers or hydrogen-based carriers, so that we can utilize these energy carriers to essentially power aviation or power our trucks, or more importantly, to decarbonize our industrial sectors, right? So for example, how do we decarbonize our steel or decarbonize our chemical plants, right? So these are really great opportunities. And the last point I want to address is also with these energy storage technologies, lithium-ion batteries, or potentially electrolytic cells to make energy carriers such as hydrogen or such as hydrogen-containing based energy carriers like ammonia. We might want to think of how we change our energy infrastructure or the infrastructure, how we make and distribute chemicals, right? For example, can we envision, instead of making ammonia in a centralized large chemical plant, and think about distributed chemical making so that we can minimize the 50% of ammonia lost in the process, so we can make ammonia utilizing electrons coming from solar wind. So thank you very much.
Great, thank you. And David Danielson?
Well, great, it's great to be home. And it's really nice to see a number of my professors, mentors, and also my former boss's boss at the Department of Energy. You know, in the spirit of the engineering training I got at MIT, I think it's important to start with a really clear problem statement. And I think the right problem statement here is we're trying to achieve a deeply decarbonized and continually decarbonizing grid down to extreme levels of decarbonization, while maintaining all the performance attributes we need on the grid, resiliency, reliability, et cetera, and doing so at least cost. And so that ends up being a really complicated problem. And when we first started RPE, the first workshop I did, was on energy storage. And I quickly gave up because the metrics were too hard to come up with, and I pivoted to EV batteries because those metrics were a lot easier. And so I think that to me was the beginning of the journey of, it's a simple fact, it's super complicated to figure out exactly how the best batteries, the best set of grid scale technologies we need in terms of storage, and exactly how those should be deployed and even controlled. And actually, I've learned a lot. You know, we've invested in Form Energy, which is a very long duration, very low cost storage company. And then what I've learned is the analytics that the private sector companies have are actually going past anything I'm seeing that the utilities have. The startups have better analytics than the utilities or folks in the academic community right now, which is kind of interesting. So they have some pretty interesting proprietary insights on the kind of battery you need. And you know, what I've seen is that you really need, like if you kind of take a Fourier transform with the variations that you're going to need with a set of storage devices, it's not a peak. It's kind of spread out. You need multiple durations of storage on the grid. And you know, for example, short duration. You know, we face pretty much lithium-ion is kind of displacing natural gas peakers already, and it's able to do that. You know, it has a moderate capex, and because you're using it so much, you can actually get away with that. It has high efficiency. So in the shorter duration, you can deal with kind of more expensive battery technologies, but they have to have a lot of efficiency, like Yetming was saying, because you're moving a lot of electrons through them. But then, you know, you're beyond just kind of a couple hours, you're gonna need many hours, you know, more than 10 to 12 to 24 hours, you're gonna need a day or two, and you're gonna need weeks. If you have an optimal set of technologies, I think you're gonna want a set of technologies that can do that. And so the way I would expect it to shake out is that we're gonna have, you know, we're gonna have a suite of technologies that some of which will pan out, and then people will figure out how to deploy those I think, you know, co-located and on the grid in a way that kind of provides for that optimal, to provide for the resiliency, reliability, et cetera, while having least cost on the system. And so, you know, one of the things I think is really interesting about the long duration, which is where we're spending a lot of our time at Breakthrough Energy Ventures, which is really kind of a day to weeks, is that, you know, it is only in the last 2 or 3 years that, because of the renewable electricity cost down megatrend, that it's even become interesting to try to develop a battery that, you know, has 40% round trip efficiency, is $10 to $20 per kilowatt hour, and has low self-discharge. That's like the crappiest battery that you could ever imagine. So no innovator would ever try to develop that battery. And so, you know, people have been working on lithium-ion for decades, and there's not a lot of white space left there, but I think there's a ton of white space for this very long duration, low capex kind of solutions, let's say 100, 300, even 1,000 hour solutions, where you have to really get really cheap capital cost. And I think Yang is making a really interesting point, and something we're looking very seriously at is going, you know, taking low cost renewable electricity beyond the grid and moving it into other sectors. And it's pretty amazing how low cost solar and wind have gotten. You know, and some of our investors are actually some of the largest solar deployment companies on earth, and they're definitely seeing in favorable geographies less than 2 cents per kilowatt hour solar without subsidies. And they don't bat an eye at 1.5 cents per kilowatt hour. And so when you get into those levels, the energy is so cheap, you can use electrochemistry to make stuff and do it cost effectively. And so I think there's a really interesting opportunity to decarbonize other sectors. I think you can use, for example, if you electrolyze water to hydrogen, store that hydrogen and run it through a turbine,